Hi, let's start for week 5 and see what is done in the week 5 of this Galois theory course, and then we'll solve exercises related to that fifth week. Okay, so let's see. Okay, yeah, okay. So let's see. So in the week 5, first of all, this was main theorem, which was, let me change my color, theorem, which was that every finite subgroup of the unit groups in any integral domain maybe, but here unit group k star of a field k is cyclic. Okay, in while proving this, many results were been encountered, like Chinese remainder theorem, in various forms. Okay, there is formulations of this Chinese remainder theorem, and this result which I was uh, using in last exercise session, that R unit if R is equal to, okay, let me write like this, R1 star cross R k star, when R is equal to R1 cross R. These kind of results, various results have been proved in the proof of above theorem. Okay, so like Euler phi function and many things. Okay, so after this, uh, about more thing, a lecture about finite fields. Finite fields. Okay, finite fields are of order some prime power m. Okay, and various discussion about finite fields. So we'll come to later. Come to this. Well, if it is needed, we'll recall some properties and group action. Little bit about group actions, arbitrary stabilizer theorems, for example, many. And then automorphism of fields, automorphism of field extension. And here we define the group, Galois group. Okay, or L over K is defined as, or Galois group over Galois group of the extension Gal L over K. is just automorphism of L over K. K algebra automorphisms. Okay, here we are considering automorphisms which fixes elements of K. Okay, so uh, then a theorem which was due to Dedekind and Artin theorem, uh, Dedekind Artin. This theorem was that for a field extension, finite field extension L over K, uh, we have a Galois group L over K. Order of this is less than or equal to degree of extension L over K. From here, it was concluded as a corollary maybe that Galois group of C over R is just two elements group plus minus one. Okay, with two other groups are basically they're classified by which is also isomorphic to Z2, something like this. Okay, or this is nothing but identity of C identity map and then conjugation map, complex conjugation. These two are elements of the Galois group. Okay, so this was one corollary, and second was that Galois group of Z. Okay, let me not write Z here. F field of P power M order, which is extension of FP. Its Galois group is just identity and this Frobenius map and its composition. Okay, up to M minus one. This as a corollary we can obtain this. Okay, so this is all things which are done in detail in the fifth week. So let's see some exercises which will solve. Okay. I hope it is visible. Let me see if class is recording. Yeah, it's recording. Okay, so let's see. First question. Okay, first question is, oh, hints are given, so we'll use them. Okay, so 5.1. Part A. L over K be a simple algebraic field extension with primitive element X. So L is nothing but K X. Okay. Yeah. Then E be an intermediate the field of L over K. Okay. Let me write K here and E here. Then L. Let mu x be this polynomial which belongs to Ex, the minimal polynomial of X over E. Then we have to show that E is of this form. Okay. So mu x E, this is already from notation. It is minimal polynomial which satisfies X and lies in Ex. Okay. Okay, and mu x e is not written like this here, in particular x power m, yeah, b m minus 1, x power m minus 1, and so on to b naught. Then we have to show that we we want to show that e is nothing but k attached with these elements b0, b and m minus 1. Sorry, yeah. So okay, let e prime be this k b0 up to bm minus 1, and note that b0 and b1 b2 bm minus 1, these are elements of e. So all the elements from e prime, they are already in e, right? So one direction is clear, e prime is subset of e, this is clear, right? So we want to show other inequality, right? So how to do this? So if you see here, L is kx, or you can write like this, kx polynomials in x, and x satisfies some mu x condition. Okay, so what is degree of extension of this? Let me write a chain here, e prime, which is subset of e, which is subset of L, e prime is superset of k. So in this we write a degree formula, which says that index of L in e prime, sorry, yeah, L over e prime is same as index of L over e into index of e over e prime. Now, if you remember in such a simple extensions, what is degree of extension L over e prime? This is nothing but degree of mu x e prime, right? And what is degree of extension here? Here also same thing, degree of mu x, here it will be e into this index e over e prime. Okay, so if you prove that mu x e is same as mu x e prime, which is given in the hint, then what will be using hint? We'll prove it later using hint that mu x e is same as mu x e prime. What we get? We get from here e over e prime. So this index is just 1, and which implies that e is nothing but e prime. And this is what we wanted to prove, right? Right? Yes. So now we want to prove mu x e is same as mu x e prime. Okay, good. So let's see how to do this. E prime is contained in e. So what will be the relation between mu x e and mu x e prime, or between degrees of this, degree of mu x e and degree of mu x e prime? what will be the relation? So mu x e prime, this degree is bigger, right? You see, x has minimal polynomial of this is from this fact. Okay, let me write here. Since uh, ex, sorry, e prime is contained in e, sorry, e here. Mu x prime, sorry, mu x e prime can have some factor in e, and then mu x e prime has more roots. How to say this? Wait a minute. Okay, for this extension over e, L over e, how to write it? E x modulo, L can be written as E x modulo mu x e, right? Simple extension. But e prime is contained in e, right? So from here, oh, yeah. What about L over e prime? How will we write it? E prime x modulo mu x e prime. Now, if we have injective map from, yes, okay. So e prime is contained in e. This will imply that e x prime, sorry, e prime x is contained in e x. And from here, e prime x inclusion map into ex quotient map, which is ex modulo mu xe, which is just L. Okay. From ex prime to L map, this composition map becomes isomorphisms when we quotiented by mu x e prime, right? That I mean this map factors through e prime x modulo mu x e prime. Then this map becomes isomorphism here, and this is quotient map. So from here, what you see, mu x e prime should be mu x e prime should belongs to kernel. Then only this map exists from first isomorphism theorem. This is just rough work I'm saying. Mu x e prime belongs to this ideal mu x e. This implies that mu x e divides mu x e prime, and then degree of mu x e prime will be bigger. Okay, okay. Let's see next. This is irreducible polynomial in bigger field. Mu x e. This is irreducible monic polynomial in E, right? And which also belongs to mu x E also belongs in E prime, right? Because all the coefficients of mu x E They are in E prime. E prime is nothing but K attached with B0 up to Bm minus 1. Okay, so this is irreducible monic polynomial in E. So this mu x is also irreducible. So this same thing is also irreducible monic in E prime, which satisfies x. Okay, then mu x E prime should this mu x E prime, which is irreducible monic, uh, minimal. Okay, this is also important. Minimal, which is this is minimal, then this would divide mu x E. Now from this first relation, star and this double star, we'll get mu x E prime, which both are monic, both are irreducible in both E prime field. So these two are equal. Now, now our proof is done, right? How? From here, if we assumed hint, using hint, E prime or index of E prime, sorry, index of E over E prime is 1. So both fields should be same. Okay. So E is equal to E prime. This is what we wanted to. Okay. So this proof is done. Let's see next part, part B. Oh, hint is again, hint is given. So I don't think we should prove this, but I will recall what is written inside the hint. L over K is algebraic extension. So that L over K is simple if and only if there are only finitely many intermediary subfields. Okay. So 5.1 B L over K. This is algebraic extension. And what is written? L is simple extension. L over K is simple extension if and only if there are only finitely many intermediary subfields. How to show this? If L over K is simple extension, then okay, let me write. I'm proving this part. Assume L is equal to K X. Or let me write like this. And X is algebraic over K. This extension is algebraic, X is algebraic. Once X is algebraic, we can write in round bracket. Otherwise, we should write. Oh, sorry. We can write it in square bracket if X is algebraic. Yes. If X is algebraic. Otherwise, we should write something like this. But in this case, both two are equal since X is algebraic over K. Okay, so we assume this and we want to show there are only finitely many intermediary subfields. Let's follow the hints. So X is algebraic over K. So this implies mu x K is a non-zero. Okay. x satisfies some polynomial and mu xk, this is non-zero uh, irreducible monic minimal. This is also monic polynomial for x. So it is non-zero, it satisfies, sorry, it has some degree, and we will follow what are its divisors. Okay, how? Because, okay, if you have L here, which is, we are assuming it is simple, so L is just kx, and we have some intermediary field E, and then here K, then E is of, if E is intermediary subfield, then E is of this form. E from part 1. Part A implies E is equal to K, some A0, AN, some N, or some implies E is of this form where uh, this A0 plus A1x and so on, AN x power n plus x power n plus 1. This polynomial is, so in the part 1, what we have seen, when we have intermediary field E and E is of this form, a divisor of, sorry, is a, its minimal polynomial is, let me write, mu x E. Okay, but we have seen this that what are subfields of L, how will they look like? Hmm? Okay, so if this polynomial is mu x E, so L is nothing but K. Okay, what should be relation between mu xk and mu x E? Their degrees, which is bigger degree? Degree of mu xk, this should be bigger, because once your field is getting bigger, this minimal polynomial can get some root and be more minimal, right? In this sense, and mu x E divides mu x k. We are using that this trick is in the first step. If E prime is subfield, then mu x E divides mu x E prime, and here k is subfield of E, so mu x E divides mu x k. So corresponding to each divisor of mu x k, mu x k is non-zero, it has some degree. So corresponding to each divisor, we will have these fields. Okay. So okay, let me write dx here, and here intermediary subfield. But notation is that say L okay. Yes. Corresponding to any divisor mu x, any divisor of mu x K, you will have intermediary subfield, right? Where if some, let's say B0 plus B1x, Bm minus 1, xm minus 1 plus x power m, this kind of divisor goes to this field K attached with B0, B1, Bm minus 1. Okay, so this map is surjective. Part A implies this map, let's say psi, is surjective. So, but you remember here how many divisors of a minimal polynomial can have? Dx is divisors of, this is divisors, monic irreducible divisors, huh? Monic irreducible divisors of mu xk. This is our notation here. This is part A implies psi is surjective because any subfield, intermediary field of L over K is of this form. So this is surjective, but you have a surjective map. So what should be order here? L over K. Order of intermediary subfields should be less than order of dx, but dx is a divisor of a finite degree polynomial. So how many they can be? This is finite. So we are done. This implies yes, up to isomorphism. Yes, up to isomorphism we have finitely many. Yeah, up to finitely many intermediary subfield. On the other hand, if you have finitely many uh, intermediary subfields, then we can assume K is infinite. We are assuming this. Also, we can assume without loss of generality. We also assume K finite. Sorry, K infinite. Because in the for finite case, if K is finite, then both side is trivially true. Any field extension is simple, and they have, because K itself is finite, so we cannot have infinitely many intermediate subfields. So infinitely many subfields can occur. Both sides of if and only are vacuously true. So we are assuming K is infinite. Now L over K, we have infinitely many intermediary subfields. So what about the simple fields, simple field extension of K? Kx, where x belonging to L. this is subset of say L over K. And because this is finite set, this is also finite. So we can assume some maximal element here. Let K X be maximal. Maximal means it does not contain any other element of this type, KY type subfield. So K X be maximal. Let me write this set as S in S, maximal in S. Then we will show that claim is that L is nothing but Kx only. Okay, if L is not Kx, then pick some element, let otherwise, if not, let Y from L, but not from Kx. Okay, what will show okay. So here, if not, let Y from L, but not from Kx, then what about this set? Kx plus Ay. Here, A is running in K. This is also subfield, intermediary subfields of L over K. And so this will be finite set. Once it is finite, then for different A, there exists A prime in K distinct such that Kx plus Ay is same as Kx plus A prime Y. Okay. Now, what you see here, okay, A prime are distinct, and these two subfields are equal, the fields of L. Now, what about this element Y A minus B into Y A minus A prime, sorry, 1 over A minus A prime. This is non-zero, so we can divide it, and this can be written as 1 A minus A prime. Inside bracket we have X minus X plus AY minus A prime Y. Okay, these two are getting cancelled, and this is what is written here. Okay, so this is nothing but 1 upon A minus A prime, and X plus A prime, sorry, X plus AY here, and minus common here, X plus A prime Y here. This is Y, and these both elements, X plus AY, X plus A prime Y, because these two fields are same, so both belongs to, this belongs to K, let me write Kx plus AY. Okay, once it belongs here, Y belongs here, what you can say, Kx plus AY, Y belongs here, X already belongs here, Y, X plus AY belongs here. Now, because Y belongs here, minus AY also belongs in this field. but this is equal to x. This implies kx plus ay is same as kxy. This is bigger than kx, right? But this is simple. So this is contradiction because kx was maximal in simple extensions. Kx we choose n it was maximal between simple extensions. Okay, so L is equal to K. Sorry. L is equal to Kx. Okay, so this is given in the hint. You can read it or you can look into this at any time when you require. In the part C, when L over K is simple, but X is not algebraic, then when algebraic is very necessary. If it is not algebraic, F, then Kx has infinitely many intermediary subfields. Okay, infinitely many arbiters. This is written here. I'm not going to write it again. Read it. Kx prime. If you change, okay, here from part A, these two are not equal. Or M and N. For different M and N, these two uh, subfields are not equal. Okay. Because X satisfies n degree polynomial here, and X satisfies m degree polynomial here. So mu X and mu both minimal polynomial are different. Okay. Okay, so we have infinitely many distinct subfields of this form. There are many, but this kind of simple extension, we got infinitely many. So that's all we required. Now let's see 5.2. Okay, so let's see 5.2. If L is simple extension, finite simple extension, finite means it will be algebraic also. Okay, so remember of degree n, this implies X satisfies n degree polynomial over K. So that number of intermediary subfields E is at most 2 power n minus 1. How to do that? Here L is nothing but Kx, which is same as K square bracket X, because X is algebraic. And what is mu xk? Degree of mu xk, this degree, which is also dimension of L over, or dimension of L. Okay, this is both are n. Okay, basically degree of mu x is n, and this is by definition. Okay, so what we have to show? Number of intermediary subfields It is cardinality of intermediary subfields L over K. This is less than 2 power n minus 1, which is again, we can just write 2 power this. All these numbers are same. L over K minus 1. Okay, so X satisfies some polynomial mu x k, and X lies in L. X belongs to L, and X satisfies some polynomial of mu x k of X is equal to 0, where mu x k belongs to kx. So by Kronecker theorem or splitting field, existence of splitting field, there exists a field. Let me write F, which contains L and has all the roots. L is just kx. So once it has x, it will have all kx, and mu x k splits into linear factors in F. Now it splits into linear factors. What will this imply? In F. So let's write mu x k as these factors: x minus x, because x should be one root there, into x minus x1, some other root, x minus, or let me write x2 here, x1 here. X1 is same as x minus xn. So that n degree polynomial, the notation is good for that. Okay. Xi can be equal to xj also. So in that case, that root xj root will occur with multiplicity 2. Okay. But here x is equal to x1 we are taking. Okay, so that x also satisfies this polynomial. Good. Now any intermediary subfield will be will correspond to a divisor, right? In this proof also we have shown somewhere this correspondence. Intermediary subfields correspond to divisors, or from part A we can just write it is enough to calculate, because since order of intermediary okay, not order of this set, which is intermediary subfields of this extension, this is less than order of this set of divisors of set of divisors of mu x k, this set. So if we show this set, it's just of or less than or equal to 2 power n minus 1, then we are done. This Okay, let's see. So how to let it is a counting method. So let me write how to count divisors of it. Let px be a divisor of mu xk and or with with when we are choosing intermediary subfield. So okay, let me see. If we add this condition with x as a root, then how to construct such px can be written as x minus x1, which is just x, and this is fixed. This is fixed factor. What about x minus x2? It has two choices: can occur in px, cannot occur in px. Okay, okay. Let me write here x minus xn. Then these factors has two choices: either to occur in px or not. Then this implies there are, because these are n minus 1 choices, okay, 2 power n minus 1 such fact. There are 2 power n minus 1 such px which uh, can be factors of mu x k. Okay, so factors means divisors of mu x. So this implies this proves our claim. Okay, so why is this needed here? Let me see. So in the first question, we have to see here, mu x e is a minimal polynomial of x over e. Then that decides what is e, and it should divide. Okay, let me explain here. If E is intermediary field, K, E, and then L, which is just Kx, okay, then mu x E divides mu x K, okay. So we are finding such, yeah. So we are picking such mu x E. Okay, from here we are trying to find such mu x E, okay, which by default will satisfy x, which uh, okay. So yeah, we are finding such factors mu x E prime, sorry, mu x E with a special property that uh, they are minimal polynomial of x. That's all. So this factor is fixed factor. Okay, this factor. Other factors have two choices. Either they will occur in this mu x E or will not occur. Okay, this is some. This will correspond to some mu x E. Okay. So we have to give a counter example that this such that this inequality can be strict. How to do that? Uh, what you will say to this? Let let this is 5.2. Continued. K is equal to Q and L is equal to Q cube root of 2. So let me write x here. Then what polynomial will satisfy x? X cube minus 2. This polynomial is, or let me write like this. This is mu x k. Can we factor it? This will be x minus cube root of 2 into x square plus cube root of 2 x plus cube root of 2 square, right? How I'm writing x cube minus y cube? This is nothing but x minus y, x square plus xy plus y square from here. But anyway, this is factorization of mu x, and we want to find what are intermediary subfield of this L over K. What is degree of L over K? This is 3, right? Because mu x is of degree 3. So we want to show this intermediary subfields are strictly less than 2 power 3 minus 1, which is just 2 power 2, which is just 4. How many subfields between q cube root of 2 between q? How many such e? Okay, so we want to count such intermediary subfields. Okay, they will correspond to, but such e will correspond to mu x e prime, sorry, mu x e, a factor of divisor of x cube minus 2 uh, with cube root 2 as a root. But you see in this factor, but uh, no factor of x square plus cube root 2 x plus cube root 2 square, no factor of them is real, is real. Real means a real factor. So that is complex. All factors are complex here. So it is something like x plus z and x minus z, z bar. Z and z bar are complex numbers. So in that sense, so other than yeah, no such a e exists. So no such factor exists. So no intermediary subfield other than q and cube root 2 exists. So uh, intermediate subfield for L, okay, this is just 2, these two, which is just strictly less than 4. This is what we wanted to solve. Okay, now we'll go to next question. This was 5.2. Now we'll go to 5.3. Here it is. Let me cut here. Or let me take this two. Okay, we'll take one by one. Yeah. Okay, so in 5.3a, how will we solve? L is finite, sorry, yeah, field extension x, y, two non-zero elements, that is invertible element, such that x to the power m is inside k and y to the power n is inside k for some relatively prime natural numbers m and n, so that x into y is primitive element of this field extension. So we have field extension L over K. Okay, x, y belonging to L, non-zero elements of L. I mean unit. Then we have to show x into y primitive. That is x into y. This field is same as kxy, kx comma y. So this will imply that x into y is primitive. Okay, so how to show this? We have already given this hypothesis that x power m belongs to k, y to the power n belongs to k, and GCD mn is 1. With this much detail, we want to show this. One side is clear. You see from here, this side k x into y. This is subset of kxy. Okay, this is clear. For the other side, what we do, we'll use the hint given that there exists. We and now we want to show kx into y contain. This is a question mark to this x comma y. Okay, for this we will go like this. There exists st inside z such that st, sorry, sn plus tn is equal to 1. And why this is so? Because GCD mn is 1. Okay, so what? Now we also x is inside this as y as well as y is inside this, then we are done. Good. How will show that x belongs to kx dot y? But x can be written as x power 1, and x power 1 can be written as x power sm plus tn, right? What else? From here, x to the power sm, because x to the power, okay, this can be written x power sm plus x power tn. Okay. Now from here, if you see here, this is inside k, because x to the power m is inside k, and this is nothing but x to the power ms into s, right? This belongs to k. What else we can write here for some trick? Let me write here y to the power n, because y to the power n also belongs to k. So, and this is not, y is non-zero. This will be non-zero. We can multiply t here, then we should multiply in the numerator also y to the power Tn into this part, which is left x to the power Tn. Then you see this first thing, this much, uh, this belongs to k. So we can write some alpha into x into y to the power Tn, right? This belongs to k, and this part belongs to this field where we want to show. Hmm. So this thing belongs to k x into y, right? So x belongs to k x into y. Same trick will imply that y also belongs to k x into y. So this thing will imply that k x comma y, this whole thing belongs is subset of k x into y, and this is what we wanted to show. So this is one direction, and this is the other direction. We have shown both. Okay, so let's see next question. 5.3a done. 5.3b. 5.3b says x comma y to indeterminate over zp. K is zpxy xp so that L over K has degree P and is not simple. Okay, what is K here? K is ZP X power P Y power. Okay, field generated by this. And what is L? ZP XY. This is our L. Now we have to show that this index L over K is P square. If you say we want to calculate this L over ZP X power P Y. L is just this, and then below this, and this extension ZP X power P Y power P. So it is this will be P degree extension. This will be P degree extension. Then total extension with this is K. Total degree of extension will be P square. So this is enough to show. This will be P square for this, enough to show ZP X power P to ZP X. This degree is degree extension. Or let me write like this: index is equal to P. But that is also clear, right? X satisfies uh, P degree polynomial, which is minimal. if you have a degree less than or equal to p, then it does not satisfy. I'm going to write what it is, uh, which is minimal. Then this degree of extension will be uh, degree of minimal polynomial. And will be of degree p. What is that polynomial? That polynomial is t power p. This p, this is in terms of uh, t variable. Okay, let me write like this: mu x. Mu x is nothing but mu x of t is nothing but t power p minus x power p, and this belongs to fp xp, right? So this is constant and this is variable, and this is p degree polynomial, and x satisfies this. If x, yeah, no, this is minimal. Okay, this is clear from here. X to the power p is minus x to the power q is not zero if p is not equal to p. So this is minimal also. It is p degree. So this degree is p, and this is now done. Okay. So this is, yeah. So total extension degree L over K is just p square. What is second question? In the second question, we have we because this is not simple. Okay, yeah, we have to show it is not simple. L, this degree extension is finite if L is simple lower k, then there are infinitely many intermediary subfields. So uh, this is, if L is simple, then we have this, and we have to show it is not simple. So we'll show there are infinitely many intermediary subfields. How will we show? Consider these subfields: E alpha, which is defined as K, okay, and we are adding just X plus alpha Y, where alpha varies from in K. These things. This is infinite set, is infinite set. These are subfields of K. So E alpha is subset of this L over K. Intermediary subfields will show E alpha. If alpha and beta are different, E alpha, E beta are different, then we are done, right? Since K is infinite, not that K is not ZP. K is Z, X power P, Y power P. Okay, so this is infinite. K is infinite. If we show uh, alpha not equal to beta, E alpha, E beta different, then we are done. Then cardinality of this intermediary subfields of L over K, this is infinite. And this will imply L over K is not simple. And we are done then. So this is enough to show alpha beta not equal, E alpha E beta are not equal. If E alpha E beta are same, E alpha if what we will have, X plus alpha Y this is similar as we did in question number 1 here. If these two things are equal, what we'll see, if two such things are equal, then K of this is same as K xy. Okay, and this is contradiction. You see why? Since degree of extension of this, degree of extension of K x plus alpha y over K is P, and degree of extension K xy from where I'm writing this 5.1 C. Right? This is part C. This is part C. Oh no, part B. Yeah, part B. From 5.1 B. Okay, so this degree is P square. So these are subfields. E alphas are subfields of so intermediary subfields of extension degree P, and they are distinct. As alpha bar is K is infinite, so for infinitely many alpha we get infinitely many E alphas, and so this proof is done. Okay, good. Now we'll see last question. So we still have time. Let me do last question here. Let K be field, Kx be rational function field in one variable, phi be a non-constant rational function. Okay, so phi is something like fx by gx, where fx and gx both are capital X. So capital X means variable and small x means some element of bigger field. So don't worry about that. If somewhere my writing is also bad in that sense. But anyway, you see it from the context, it will be clear. Phi is some rational function like this. FGR with GCD1 and G is non-zero. Then show that field extension is finite. So 5.58. We have to show K phi to this extension K x is finite extension. Now because here x is appearing in field also, so capital X is not we are taking as variable. So for that we'll write y. Okay, y will be as variables if we take. How to do that? Hint is given. X satisfies this polynomial. F of y minus phi g of y, and this polynomial belongs to k phi this variable y as variable. Okay, good. So what is degree of this polynomial? I'm writing this as mu capital X. I'm not writing what field is. Okay, mu x, degree of mu x is maximum of degree of f and g. Okay, because this is constant. Phi is just constant only. So this will g of y and f of y. This polynomial will decide maximum of this degree f degree g. Degree of f will f and g will decide degree of mu. Okay, x satisfies this polynomial. So this polynomial over k phi. So this degree of field extension is nothing but okay. If it is irreducible, then yeah, because we are also assuming GCD FG is equal to 1. Then we'll show that mu x is irreducible. So once it is irreducible monic, it might not be monic, but its irreducibility will show that degree of extension will be degree of mu x. How to write this? Yes, x satisfies this, so we can write it as f x minus p g x is equal to 0. From here, fx is equal to p g x. Oh, now this implies that g divides f, right? GCD of two polynomials, if they are equal. Okay, for time being, let's say we have this. Okay, even if we don't have, mu x, this mu x might not be minimal polynomial satisfying this, but mu x, okay, mu x k phi is divides mu x because this is minimal polynomial and this is satisfies x. So this mu x k phi divides mu x. So in any case, degree of extension over degree of, sorry, this is equal to degree of mu x k phi, and which is less than, which is finite anyway. Okay, that's all. These are some polynomials of some degree, but it is an exercise. Let's say exercise you want to solve. Mu x k phi is same as mu x. Okay, mu x irreducible. So this mu x is irreducible over k phi. Then this will be minimal also. We can make it monic by dividing monic factor, means leading factor. So that does not matter, but you saw this up to some unit, some leading coefficient, up to some leading coefficient, maybe some unit. I'm not writing that, huh? Some alpha. So yeah, this degree of extension is finite, so that this is moreover uh, this is same as degree of phi. Degree of phi is this maximum, which is, I'm writing here. This is also denoted degree of phi. So does not matter. All of these things are equal. So once these two things are equal, their degree will be equal, and this will be degree mu x or degree phi, whatever we write. Now, so let's see part B. EB intermediary field, and so that kx over E is finite. Kx E k. E is some intermediary field, and kx, this is finite excellent. How will we show? Let E is k, it is not k5. It is the intermediary field not equal to k. This is between kx and k. If it is equal to k, then degree of extension will be 1. So that will be finite. But if it is not equal to k, then let phi belong to kx minus e. Okay, then what will happen? Kx over e, we should show kx over e is finite, right? Okay, so I'm choosing wrong. Phi belonging to e minus k, because e is not equal to k. You can take that. Then uh, k phi, this degree of extension kx over k phi, this is finite. But what you know, e kx is subset of e. Sorry. K phi is subset of e, and e is subset of kx. This implies kx over E. This is also finite degree extension. Okay, so today's class done. Okay, if you heard out, you can ask me in this section. Okay, let me stop recording.